what this is all about. So we are talking about design principles, and particularly to develop precision products or precision machines. So I think one of the things I asked in the very beginning, and one example I gave you, what's so important about it? Why we are talking about this at all? So I gave you one example here, and I was talking about, like, okay, you see here is a very mundane thing, very it's a household thing, and you see house, and it's easy to find three-legged and four-legged table. So yeah, many times we just say that one is a coffee table and one is tea table. But okay, let's not talk about this, but let's talk about this three-legged and four-legged table. So can you tell me, like, in terms of stability or in terms of deterministic behavior, so which one you find that is a better? To any of you, if you can just switch on your mic and tell me.
Four-legged, I guess.
Yeah, of course you can guess. No problem.
Sorry, sir.
You can guess. You can tell me which one is better, three or four.
Four, sir.
Three.
Four.
Four. And why you think so?
It seems more stable.
Okay. Anybody else? So okay.
Four-legged, sir.
Four-legged. So I think now I'll deliberate a little bit. So whenever you have, okay, most of the time we see four-legged table in our homes, right? And then the very new furniture, when you get it, or even the old furniture with the four leg, if you get it at home and if you move from one place to another place, what will happen? What is the first thing you encounter? Do you find any problem in that? So many times what happens whenever, if you if you're getting a new table and if you're moving around, what happens that it doesn't fit to the surface. It just starts wobbling. So then you adjust or put some kind of seam or some fold your paper and just put in one of the legs, right, to make it stable, I would say. So what happens is you keep adjusting. On the other hand, what happens if you have new one, and suppose if it's not sitting on the surface, many times what you do is you put some on top of the table so that it deforms and conform to the surface. So here also what you are doing is you are depending on the flexibility of the surface, or I would say the internal degrees of freedom. So you assume that it will deform and then it will sit on the surface and then it stays there. But again, what happens whenever you move it away, depending on the surface, you may have to adjust it. And that's the reason, like these days, if you buy any electric equipment, whether it's a washing machine or freeze or any storage thing, you need to adjust. You have the four legs and you have adjustment, and you need to adjust them. So that's a problem. To me, it's a problem because every time you move around, you have to adjust. Can you just answer me? So moving forward, what you see is if you have this three-legged table, one good thing is no matter where you move it, it will not wobble. it will not rock. So even if it's uneven ground, moment you move it, it will stay there. It may be tilted, but it will stay there. It will not rock. So from precision point of view, what we say that the three-legged in this case is stable. It's a deterministic. So suppose you have a kind of adjustment at the bottom, whether in 3 or 4. In 3, you can precisely adjust it and bring it to a level. For 4, for the 3 you can adjust, but 4 one has to always align, comply with the other 3. So you need a new constraint or new adjustment. So how to look at it is, what you can see is, if you see here, if these are the point contracts, if I just mark it. So these are the contacts. So in general, if I just connect them, so in this case, what happens at the point of contact, in case of three-legged, you can always define plane, and it's a unique. So there is one plane passing through all these 3 points. So whether you are moving to any ununiform surface or like non-uniform surfaces or any plane surfaces, virtually you have a plane defined at those 3 points. One on the surface and one by these 3 points on the legged, on these legged contacts, and they are conforming. So once they conform, they stay. So it's a uniquely defined. On the other hand, if you take these contact points, 4 contact points, now my question is, can you define a unique plane passing through all the 4 points? Or how many planes you have to define? So once you have this, and if there are some inaccuracies in this so link length or this cable leg length, necessarily all the 4 points lie in a plane. Or if I say that, suppose if I take these 3, if I want that this table should be stable, I want that this point should lie on this plane also. It means I'm adding extra constraint, and the plane defined by these 3 may not be same as. So I call it 1, I call it 2. So similarly, there will be many planes defined. So if you take these 3, then there will be another plane. If you take these 3, there will be another plane. So there are multiple planes. And in order it to work properly, all these planes should be coplanar. So there is the additional constraints. And that's the reason when we go for this kind of design, the 4-legged, what we call it over constraint, we put additional requirement. And it means, in this case, all these 4 legs should be precisely made with certain tolerances. On the other hand, if we have three-legged case, we may not have that kind of requirement. We can have 3 legs, and then we can have adjustment and we can adjust it later precisely. So usually is the belief is that when we go for precision machine design or any precision engineering, we need precise component, but that's not entirely true. What we see is, if you follow the principles of principle machine design, many times it's possible to design precision precision products with less precise components. And that's the debate we can have, and we can continue. So we'll continue with this one. So this is one case, very simple case. Next one is, I showed this example. And here again, I would like you to now deliberate. Or like in the previous problem, can you, do you agree that the three-legged will be more deterministic and stable design compared to the four-legged? Please switch on your mic and the comment, if you can. So I'm not getting any response.
Can you repeat your question, sir?
So I'm just asking whether you are convinced that the three-legged will be better than the four-legged one in this case.
Yes, sir. By this definition, like there are multiple planes, so it. But in realistic way, it seems that four-legged chair is more like stable.
Yeah, but it starts rocking. And okay, many times there will be question about how about the stability or like toppling. So that part we have to take care, and that will come later. Okay, but in terms of deterministic behavior, I think you agree that the three-legged will perform better, and you need less adjustment, right?
Yes, sir.
Yeah. So I want some so going on similar lines. What do you think here? So again, it's a very simple problem. I hope everybody might have seen this clay chula. So maybe I change the color. Pick up some different color. Okay. So what you see here is again, there is one here, there is one here, and there might be another one third here. So if I, yeah, and there might be another one third one, right? So this whole patella thing, or the whatever utensils you have, they are sitting on 3-point contact. And in this case, it's in 3D, right? And what you see here is whether it's a flat surface or curved surface, they will actually sit on these 3 contact points very easily. And so same you see here. And then, okay, you have another one, and you may have another one. 3. So they don't rock. They just sit there, and then you can easily like do the cooking. And what you also see here is they are just clay. They are not metallic or any engineer thing. It's just clay. Clay, and people use it, and maybe people from village, they can easily correlate with this. But yeah, if you are not aware of this, maybe you talk to your colleagues and see. On the other hand, if you see this part, the modern one, now is have, so not necessarily here, but we're talking about these surfaces also, right? Sometimes it's and you may see these days whenever you put your utensils, they make a lot of noise. They rattle and they wobble, and it's mainly because there are four contacts, and you are not just talking about this point contact, but you are talking about the surface contacts. So how to make them conformal? So it's not easy, and it's a lot of over constraints. So whenever if you put certain thing on top of it, it doesn't comply to the surface, and many times you have that. Okay, maybe because of the symmetry, people like it and want to use it, or maybe you have the notion that more contact point is a better. But on the other hand, if you see this, and you can see amount of this thing, uh, so you can put a lot of utensils and it still is stable. So many times you have to talk about how many contacts should be there, and that's what we will talk about in this course. How many contacts precisely? Suppose if you are bolting it, how many bolts? Whether two is enough, or three is enough, or four is enough, right? For proper securing. And another thing is what happens if it's more than necessary. So exact constraint means you constrain them to the extent it requires, right? And we'll talk about those things in detail in coming lectures. So many times I also get questions and some feedback, and it was mentioned that don't get enough practice on the mathematics or the calculation part. But in this course, what I want to emphasize that any kind of calculation are very simple, and you have done in your UG undergraduate level, and it's just like your force calculations, or you need a little bit of mechanics materials, or maybe just beam equations, and you have to work with that. So wherever required, I'll go through it, but it's not like very involved or very sophisticated. So here we talk about those principles, use them to design precision components or precision modules. So for instance, here, this is my work, PhD work. And here what we intended to do is we wanted to design a module or a system where if what you see here is explore view, and this is the top plate, and there is a tube here. So what I wanted to have is if I insert a flexible instrument, so any kind of force, any kind of interaction between the tube and the instrument, I should be able to measure. So I think you be knowing, or you may later realize that you have total 6 degrees of freedom only. If you take any rigid body in a space, it has 6 degrees of freedom. And likewise, if it's a constraint completely, you'll have total 6 forces only. 6 forces means 3 forces, translation forces. So that is Fx, Fy, and Fz. And there will be 3 moments. So if you design properly, and if you have 6 forces, you can easily resolve into 6 forces, linear components only. So here, what you see here is actually you have a suspended platform. Why we call it suspended, I'll come quickly. So there is a bottom plate, then the bottom plate, this the blue box, is supported on 3 wires only. So it's like a steel wire, 1 millimeter cross section and 30 millimeter length, 30 or 25, something like that. So 3 wires. So you may think that it's a very, it may not be strong enough to take it, but just assume that it's there, and I'll explain to that. So there are 3 wires supported, and at the base we have a load cell which can measure the force along the longitudinal directions. Similarly, on the x direction we have 2 more, and then in the y direction we have a z. So in z direction we have 3 wires, in x direction we have 2, and in y direction 1. So we call it 3-to-1 configuration. And here what we claim that any force acting on the blue block, which is this block, I will be able to measure precisely using the 6 load cell which are sitting at the bottom of these wires. And the forces are along the longitudinal direction of the wire. Okay, so we'll just deliberate on that a little bit, and how to calculate. and how to resolve. So these are the details, and so this is the functional element, and these are the mechanism to prevent it from getting damaged. And there is a load cell here, so it's a sandwich. The load cell is sandwiched between. So this is the configuration, but this is the concept we are talking about. It's a detail now, and you see here is okay. These are 1, 2, 3 from the base along the z direction. In the x direction, 4 and 5 and 6 along y direction, and these are your geometry. So if you see from this side, so which one is the front view? 1, 2, 3, right? So you are able to see from this side 1, 2, 3, and then this distance is b from the. So you can see, and similarly from this side it's a 2a. So if so mathematics generally what we were looking at is you may use MATLAB, and you may have to write in this form. So fx is equal to afn. So fx is a matrix here. So fx is like, it's a vector. So fx, fy, fz, mx, my, mx, my, and z. So this is your, and you want a relationship here, and Fn is simply the forces along this longitudinal direction. So F1, F2, F3, F4, F5, F6. So actually here now you have to find 3, 4, 5, 6, 2, 3, 4, 5, 6. So it's a 6 by 6 matrix here. So you have to find a relationship. So do you think it's possible to find from here? So the how to start with this, it's very simple. So suppose if the force coming on these wires is compressive in nature with minus sign, if it's in tension, then it's a positive. So for instance, just start with x, y, z here. So fx. So if I have a fx component, fx working, will be resisted by, not by 1. There will be no component along 1, 3, and 6 because they are all orthogonal, right? But they are in plane with 4 and 5 and in the same direction. But if you apply fx, it will try to compress. So it will be minus f4 minus f5, right? Similarly, if you have fy, what will happen? If you have fy acting, it will compress this wire. So the component will be only f6. Similarly, if you take fz along the upward direction is positive, so it will be all tensile in nature. So the component will be f1, f2, f1 plus f2 plus f3. Now what about mx? mx is this one, and now this direction. So maybe double put. So in the x direction, if there is a moment, right? So maybe it's clear from here, from this one, this diagram. So if you have mx acting, what will happen? Along 1 is passing through the same plane, so there will be no moment because of 1. 4, 5, 6, they will not do anything because again they are They don't contribute anything in MX. But 2 and 3, so 2 will be in tension and 3 will be under compression. But if it's a F2, so this will be in tension. So okay, F2 tension and multiplied by B is in tension. Otherwise, one is in compression. So it will be minus F3 B. So likewise, you can write My, Mz. So I'll ask you to check and then work. But ultimately, you will find that you will be able. So you can see from here. So if you write Fx, M minus, so one component 0, two component 0, three component 0 is minus 1, and then again 0. If you talk about Fy component, it's all 0, 0, 0, 0, 0, minus 1. And then if it's Fz, this 1, 1, 1, 0, 0, 0. So likewise, if you keep going, continue, you will be able to find. So you can see minus 1, minus 1, minus 1 here. Fz 1, 1, 1. For Mx, it's 0, B, F2, and F3 minus, right? I think that's what we got. Yes, that's what we have. B 0, B, and minus B. So that's what you have. But similarly, you will get the matrices. So this is the thing we might be interested to know. So there can be a different configuration. So suppose if I in 2D, if it's just like I say this is your block and this is suspended on 2 wire and then 3 wire and supported on the ground like this, right? And I say 1, 2, 3. Can you write what will be the, so here suppose I say XY, any direction you can say X, Y. So in this case, and this will be theta direction, or you can be. So what will be Fx? So it will be matrix. So if I say what will be this matrix, and this is Fn. Fn is 1, 2, 3, and this will be here 3 by 3 matrix. So I can ask this kind of questions. Sometimes it can be also like not like in the orthogonal direction. What happens if it's in the different direction? But I think before coming to that, I have to explain some more things, and we'll talk about this. So let's continue, and this is the second part of the lecture today. So what we are looking at in this course, and when we talk about design of precision machines, again I'll repeat. I showed this slide in the last lecture, but what is important, what we are looking at is high precision and fast moving mechanisms. So what are the design concepts and how to achieve that? And of course, through creativity by examples and giving some insight, guide creativity, and also knowing the hidden properties and what people do in the field or in the actual designs. And a lot of them from Phyllis, but now I can also claim that many ideas, many concepts are also from what I'm doing for last few years, last 7, 8 years here. So designing is, which many times is asked, and not only students, but even the practitioner, they ask like, how to do that? Is there any way? And what you see that it's a cyclic process. So intuition, creativity, experience, analysis. So you design something, right? maybe following some principles, or it may be just intuitions. uh, and you do the analysis, you have the experience, and again, so it fits to each other. mm. So creativity, intuition, you are talking about idea generation, brainstorming, review, examples, new conditions, right? New conditions with new requirements, new constraints, right? And under those boundaries, you try to come up with the new ideas, and you then brainstorm whether these things are good or bad. You also review, you try to calculate, you try to see. It's not just about making some cats, but also looking at the feasibility, looking at the some calculation, whether it can sustain. If you have some doubt, you do some calculation. And also then, okay, you do modeling and simulations. So hand calculation, but also it's the things might be very complex and may not be able to just do calculation, but you have to also see whether it works in reality, not in reality, but in a simulation environment. And then you also try to compare the specs. So at design phase, you have certain specification requirements, I would say, requirements, and then you convert them into design specification. Design specifications, and then you compare with them. You also apply, so with experience or with some guidance, there are some rules of thumb, and then you practice them. You have some learning from your previous work, some failure or some successes, so you try to, then better, okay, what to do and what not to do. Okay, you have to also validate, so you have to do a lot of measurement testing, and then again review, and whether things are working and it's not working. Okay, so it's a cyclic process, it goes, so it doesn't stop, it keeps on going. So what you see here is yes, you guys will be playing a designer's role, and what are the considerations? And I think earlier I said customer specifications. So many times you are looking for customer specification. What he says is just a starting point, merely, just a starting point. Designers' proficiency and ideas must help to improve the quality of the specification. It's very important that you should know what are the specifications, what are the real specifications, because customer specifications can be very vague, very abstract. So if you have experience and if you know like how to ask those questions so that you the real number, then that helps. So, and other is responsibility is to explore new alternatives in order to improve on performance, and again, functionality over cost. So once you have these specifications with you, then you will start looking for the design concepts, alternatives, and then how to improve the functionality over cost, because cost is always there, cost is always involved. So what we'll be looking at is, okay, how to achieve. So ultimately we are looking at achieving precision, or maybe looking high precision or high speeds. So fundamental concepts, one of the key concept is your controlling degrees of freedom. So it's not degrees of freedom we are talking about, but how to control them, right? Flexure mechanisms or compliant mechanisms. So many times we use them because either it's a very miniaturized application, so very of the order of micron, or maybe suppose if a chip level design, then there's no other way, you have to go for compliant mechanisms. On the other hand, you also realize that many times these motions, rigid body motion, can be very small, limited to few degrees, or it can be of the order of few microns or even few millimeters only. And in that case, there is no need to put ball bearings or some kind of revolute point, but that can easily you do using the flexure mechanisms. One of the problem in achieving high precision is friction. So how to, well, we always try to avoid, if it's possible, don't use it. Please get rid of that. If can't do that, then manage it. How to manage it? Expressive and micro slip, they also give rise to backlashes, and that's not very good if you are going to design a high precision system, which can, if you are targeting some micron level kind of accuracy. What kind of actuator sensors and materials, slideways, and some dynamics we'll be talking if we have time. But I think these four will be very important in here. This one optional, I think once we have time, and we'll quickly try to go through it. And if you are involved in some design later, then you will be dealing with all these comments. So precision engineering is, in general, is a very vast field, and the focus is in getting high precision products and high precision processing. So it also talks about developing those systems, right? So suppose if you need a very precise components, so in some application you may need it. You may need very good surface finish. So how to achieve that? How to achieve them? So it's not just processes, but also talking about the design of those systems. So precision engineering in general comprises of design of precision, design for precision, and that's the design philosophy we'll be talking about. Of course, many times it requires optical and mechanical methodology. Methodology is basically the measurement system required. So it always works in feedback, and then you need to measure whether you have achieved it. And many times you also talk about precision manufacturing, precision processes. But in this course, we'll be talking about design for precision. So all these things are in that review note. Please go through it, and there are a lot of interesting material. I'll quickly go through some of them so that you can digest the concepts and be for the. So I'm quickly moving and maybe just highlighting a few things. So one of the things these days, what you also realize that we are talking about total design. It's not just mechanical design. You're not just talking about CAD and putting them together, and you have very nice CAD design and building only the mechanical system. But we're talking about materials, mechanics, electronics, control, thermomechanics, dynamics, and software. So everything is included, because just a mechanical design will not give you that precision. It's in a loop, and that's why it's called high precision mechatronic design. And why it's important is mainly because of high precision accuracy machines, instrument, and consumer products. These days, you need this. And one of the way to just appreciate is how you are able to put that kind of memory in your phones, and that in the beginning days it was not possible, but now you are every new version you have updated hardware. How is possible? They are the physical system, and somebody is doing it, and if it's only possible because somebody is able to make high accuracy machines and instruments, right? And that leads to very good consumer products. And again, yes, many developments are because of this computer technology, data processing, data storage. These are the key factors which has maybe in future there will be some more technologies added to that. Metrology, one of the key components. So just go through it. Precision manufacturing, of course. Sometimes we need a very high tolerance components, and we need these processes. So what we need to understand that this, if we go if you go for precision, so this is a very old chart. It's by Taniguchi, and we just talk about trend in precision machining. And what you see that if you're talking about 60s, 80s, or 2000, so see these lines. So normal machine over here in 80s it was 5 micron, 2000 we were talking about 1 micron, and now we're maybe here, right? So you can imagine where you are going, right? So now 2021, huh? So you can imagine what is the, even the normal machining is slowly decreasing from 5 micron to 1 micron to okay, some micron level. Precision machining, it was 0.5 in 80s. In 2000, it was below zero point 0.1 micron, right? High precision machining, 1980s, you were talking about 0.05. Ultra high precision machining, extremely accurate machining, we are talking about this number. By 2000, you see these numbers. Yeah? So by 2020, even with the normal machining, is already maybe here. We are talking about this number, which is 0.01 micron, right? Normal machining. So what was fine earlier, maybe normal machining here in 60s, okay, may be achievable by some adjustment, some bolting, something. But I think when you, even the normal machining, normal machines, you should be able to achieve this kind of precision. And it was, you can see here, it was already an ultra high precision machining thing in 70s. In 2000, it was high precision machining. And in today's time, it's already normal machining. You are able to achieve through normal machining. So if you have this kind of requirement, do you think it's possible by just going through conventional machine design, what we do in design of machines or in at UC level? It means we will need to learn these concepts at least, so that even the normal products what we are getting these days, they should be able to match those requirements. Otherwise, we cannot compete with the world. We cannot compete with the Japanese or European or American companies. And it's very important to understand what are these philosophies, how to achieve them. And the irony is we are still here. We are still using the technologies which were in there in 1960 for normal machining. That's what we are teaching. We need to understand how to get this one. And that's why it's important that we should unlearn few things and learn new philosophy, new design principles. Okay, so this is one of the things, so that you realize that what is what. When you're talking about design for precision, we are talking about total design methodology. And then what we also want to have is, because the costs are involved, so right the first time, and we also talk about predictive design. We do a lot of modeling, a lot of analysis, so that we know how it will perform, how it will behave before we even start building it. We don't build and then start analyzing. We first design, we first conceptualize and do all the analysis beforehand, so that we know what kind of performance we should be able to get. And then we build and then again call those specifications. So what are the elements if you want to design some precision products? What are the elements? What are the key things we are looking at? So mainly we are talking about the deviations, right? And some definitions, very important: accuracy, uncertainty, and these three things we'll be talking about: resolution, repeatability, reproducibility. So just go through it. Very simple example. Suppose if you have this, so maybe it can be elaborated with respect to suppose if you are doing firing, or even suppose just moving your tool from, so you are supposed to move from this point to this point, right? So every time you give, so resolution is what? That's the minimum, the smallest step you can take, right? So every time, so you are here, you intend to move there, but you can land anywhere. So you can start from anywhere. So this is the scatter for this point, right? So you give this number in your control input, but your tool is going to this location. You can go to anywhere. And this is called the repeatability. This is the repeatability. When you take one more step, you will reach here, but again you have this repeatability. This is the resolution you are talking about, right? Accuracy is, this is the target point. This is where you wanted to go, but you reached here, right? But one thing you realize that every time you know that you are here and you make a move, you reach here. So the resolution, right? So these points, accuracy, you can always work with respect to repeatability and the resolution, and whatever offset you can through the control, you can offset it, right? But you can reach here with this uncertainty, repeatability. So whether you reach here is a question mark, because you always have some number plus minus this, and this plus minus this number. You can't have this number. You always have this number. So actually what you want to reduce is this repeatability. If you can shrink this one from all the direction, you have a better accuracy. So what you want to have is better repeatability, less noise in your reading. So of course, when you want to achieve this final accuracy, you can always talk about the geometric deviations, that is because of the geometry, kinematic geometry, and the dynamic effect. So it's a moving, accelerating, the stiffness will come into picture. So what will be those deviations? Okay, you can go through all these. Also, yes, so we'll talk about form closure and force. It's a very good concept. Form closure and force closure, and why it's important. Uh, we'll be also talking about the kinematic and semi-kinematic design. What is that in the coming lectures? Yeah, so when we are looking at the principles, there are few key concepts we'll be looking at. One is Abbe Principle. So in physics, probably in measurement, we'll talk about that, but it's very important when we develop this kind of system. Kinematic design, so it's basically degrees of freedom we are talking about. The thermal stresses, if there is any heat source, that can also lead to a lot of deviation. So we need to understand what is the source, and what is the thing, and how it's moving. A structural loop, we also call it load path. What is the importance and why we need to understand that is a very important measurement. Drive of offset, force compensation, symmetry, and repeatability. But I think this key concept we will be talking about. So Abbe principle, basically what it says is, if any displacement measuring system should be in line with the functional point. I think best way to understand is this one, the caliper versus micrometer. So what you see here is there is one caliper here. So micrometer we call it, and this is caliper. So caliper, here you have the scale or dial case. So here you have, or here you have the dial case for the measurement, right? But here you are measuring it. So there is the offset from here to here. But here what happens? Here you have the measurement and you are measuring here, the same line. So what happens here? The accuracy is much better. But here, because of this, if there is any deviation, this theta, that will lead to errors. So if there is some clearance, there is a gap, what happens? It tries, moment you apply some force, it will deform, and then this is the error you get. So caliper is not, in terms of precision, if you're talking about, you go for micrometer, not the caliper. And these principles can be used for even measuring this coordinate, it's a CMM machine. So what you see here is this point and this axis, they are in line. It's not offset. So suppose if XYZ configuration, if you say table, I think there is an offset, and because of that offset there will be error, and that's called Abbe errors. So this like in 2D, and this figure in 3D. So kinematic design, how Maxwell has defined, what do you mean by kinematic design? The pieces of our instrument are solid but not rigid. If a solid piece is constrained in more than 6 ways, I think this is very important, it will be subject to internal stress and will become strained or distorted. This in a manner which, without the most exact micrometrical measurement, it will be impossible to specify. What it says that any object, if you take any rigid object, so you cannot constrain it more than 6, because it has a 6 degrees of freedom. So it can constrain it by 6 means only, 6 ways. If you do more than that, they will start all the contact point or the boltings, they will start fighting with each other, and because of that, the body which was constrained, internal stresses will be developed and it will deform, and that deformation you may not be able to measure. So if you cannot measure, you cannot accurately say whether it's a good or bad. Very good example is, so suppose if I have to align these two components, I don't know whether you see it. Okay, maybe after the lecture I will show you what is this. So let me finish first. So the basis, so what is said that kinematics evolved from mathematics, and is hence somewhat idealized in its component, that is rigid bodies, straight lines, perfect circles, point contacts. So here you assume that it's a rigid body, things move in a straight line or perfect circles, and there are point contacts, right? Nevertheless, it is a good starting point for mechanical design that is correct in principle, right? You all know this is not possible. Nothing is rigid. No, there is no point contact. But what it says that at least it's a good starting point, because you are starting with ideal design. So the basis for kinematic design. So whenever if somebody mentions what is kinematic design, the basis is constraining the right number of degrees of freedom, translation or rotations. So whatever is required, if there are degrees of freedom, constraining it properly. That's the basis of this design, kinematic design. So I think later we'll be talking about the flexures. So I already mentioned about wire flexures, pin or wire, right? So cylinder rod, this is folded leaf spring. So it's a sheet and folded. So this is equivalent, and this is also equivalent to this for cylinder rod. So this give you one constraint along this direction. So if it's connected, it can move in all the direction. It can move. So what we are talking about the instantaneous motion. It can even turn. But it cannot move in this direction. This is not possible. And that's what we have to learn. Okay, when we are talking about constraining degrees of freedom, what does it mean? And similarly, we can create a different degrees of freedom systems. We'll come to this. Thermal loop, of course, talking about the heat and then design. So I'm quickly moving. These are all in that review paper. So please read it. Please go through it. I may take a quiz. So these are the principles we are talking about, and we'll go. And then the features we'll be talking about, the stiffness, bearing systems, flexures,